Hello everyone. I'd like to begin by having everybody picture their grandparents and their parents. Oh, sorry, I got to press it. And then I'd like you to consider that 1 in 3 Australian adults over the age of 65 will experience at least one fall per year. Falls are serious and they can cause injury or even fatality, and they can scare entire families. I know this as personally my grandmother has had a fall this year that scared our entire family. But she is not alone in this experience. In fact, in South Australia alone last year, 22,500 people were admitted to a public hospital after having a fall. And this number is only predicted to rise considering our ageing population. According to the Australian Bureau of Statistics, right now 1 in 7 Australians are over the age of 65, and by 2037 they believe that 1 in 5 Australians will be over the age of 65. Now I don't expect you to read this great big table here. The reason I include a risk assessment guide is to showcase that falls are multifactorial. Things like visual impairments or your environmental hazards or even your footwear are going to influence your risk of falling. One of these factors is somatosensation, which is a person's perception of touch and their awareness of where their limbs are in space. Somatosensation is known to deteriorate with age, and with that there's an increase in postural sway that leads to a poorer balance control and gait. One way we can enhance somatosensation is through the use of stochastic resonance, which is a phenomenon where a certain level of randomized noise can actually enhance the detection of weak signals. This seems counterintuitive, so I've set up an example to try and explain it. Here I've got a person being prodded with a monofilament on the toe, that's the little orange stick thing, and it's producing a pressure stimulus that you can see on the graph here that's below the sensory receptor threshold. So this person is unable to feel that prodding. If I add noise to the system, you can see that the noise will follow that subthreshold stimulus, and it will get slightly closer to the receptor threshold. If I go overkill and add too much noise, you can see that the noise is crossing the receptor threshold, but it's kind of random. So the person's actually just feeling the noise and nothing more, really. If, as anyone who's read Goldilocks will know, there's a point that is just right, where the noise will actually be consistent with the subthreshold stimulus and cross that receptor threshold in line with it, meaning the person's actually able to perceive that prodding now when it's on or taken off. Stochastic resonance has been shown in literature to have the potential to improve balance control by enhancing somatosensation. However, to date, the systems that have been able to demonstrate this are these large, bulky desktop computers that are really only suitable for use in a laboratory environment. If we want to see the potential benefits of using this for prolonged periods of time, and more importantly, get it into people's homes where it can actually help them, then these systems need to be condensed down into a smaller package. So that's exactly what I set out to do. Here I have the block diagram of my design, and I'm going to take you through some of the key features of what makes this a good design. Firstly, to keep it minimally small, I decided that I would remove any kind of control interface from the actual device and put it on a PC and have this PC graphical user interface to control it. It would then wirelessly communicate the stimulus parameters, the amount of noise that's being sent to a person, via Bluetooth to the device, which would then run this stimulus until it's either switched off or the value is changed. Finally, a very important key feature here is the high voltage current pump and the high voltage power supply. The current pump is essential because it works to change the voltage depending on what resistance the skin has. So it changes that voltage accordingly to make sure that it only ever delivers a maximum of 1 milliamp to the person. This is what keeps the device safe. The high voltage is needed because the skin impedance can vary greatly depending on where you're stimulating on the body, person's skin dryness, etc. And so you need to be able to have a high voltage range to accommodate for high resistance ranges. Here I have some of my printed circuit board designs. The key constraint when designing these printed circuit boards was all about size, keeping them small. And you can see that I've got 2 examples here, and the high voltage current pump was actually the largest at about 65 millimeters by 32 millimeters. And as you can picture, that's pretty small. It's about the size of a matchbox, really. I validated these designs by comparing doing some tests and comparing results to those published in the literature. Here I have one example where I was drawing current from the high voltage power supply from no load to 20 milliamps, And then on the bottom, that's mine at the top graph. And the bottom graph, I compared this to a paper that used a very similar circuit with a high voltage power supply. And you can see that they're very comparable. They have the same sort of linear drop as your current increases, the voltage drops. The user interface that's located on that PC is actually really simple to use. So the operator sets up an initial stimulation that the person can feel. And let's say we're in a clinical setting, so I'm the clinician and the patient sitting on the other side. I set a first stimulation that they can feel. And then I've got the option to reduce or increase in predefined steps of 15 microamps each. The options I have is to reduce by 4, increase by 2, or increase and decrease by 1 step. And the idea, which you can follow from this descending staircase on the bottom here, is that I ask the patient, can you feel the stim? And they go, yes. And so I decrease. Can you feel the stim? Yes, decrease. Until you get to that point where they say no, and then you reverse, go up. Can you feel it now? Yes, no, yes, no. And once you've had enough reversals, you can safely say that we've found that Goldilocks sweet spot where the noise is just right for that person. Now, the device I designed will only be used in a research context, but the commercial potential for a device like this is already apparent. Here I'm showing a similar device called WalkAid, which is a functional electrical stimulator that uses electrical stimulation to actually cause physical muscle contractions to correct problems in gait. This is mostly used for people that, say, have had a stroke or something similar. The big separator for devices that use stochastic resonance is that stimulus is sub-threshold, so you don't even feel it. Whereas these will cause perhaps pain and discomfort associated with the shock. My device, you wouldn't feel. You'd put it on and it would just silently do its work, improving your balance control without you even having to worry about it. Some final thoughts. Well, assuming none of you in here are lobsters, every one of us ages. And as I said at the top of the presentation, 1 in 3 people over the age of 65 will experience one fall a year. So I think everyone has to ask themselves, how lucky do you think you will be? How lucky do you think your friends and family are going to be? I know personally I don't really feel comfortable with those odds. And wouldn't it be great if the solution was as simple as remembering to put on your stimulator when you put your watch on in the morning? I think that'd be pretty great. That said, I'd like to thank you all very much for listening.
Thank you.
If you have any questions, I'd be happy to answer them.
Okay, you've